Hello, my name is Cory Owens. I'm the State Soil Scientist for the Oregon Natural Resources Conservation Service. I am also our co-coordinator for our soil health efforts here across the state. Today I'm going to present to you the Pacific and Mountain West Nutrient Cycling Soil Health and Food Safety Virtual Conference about soil health and an introduction to soil health. This is going to set up the stage for the rest of the session that you'll be watching today. So with that, I will start. All right, so whenever we want to talk about soil health, it really is important, and why I'm doing this presentation is so that you all can be on the same page when we think about what does soil health mean, what do we mean when we say soil health. And to really have that conversation, we first got to think about what we want soil to do for us. Why do we want a healthy soil? What does that matter? Well, what do we want soil to do? So there are some very important soil functions that many of you have heard this before, many of you have heard this talk before, but I just want to key us back into why we care about soils and how they fit into the ecosystem. Because soils do some pretty important stuff like support productive plant and livestock. They're pretty crucial to be able to resist erosion and be stable. We need soil to stay where it is so we can do things like grow food in it or fiber. We need soils to cycle nutrients internally. We need them to provide the plants and organisms in them with the nutrients they need to flourish and live. We need soils to let water quickly into their systems, and we need it to, in most agronomic situations, we want that water to drain away. Of course, if we're restoring wetlands, we want that water to stay. But in most of the systems that we're going to be talking about, we want that water to drain well out of the soil. And we want enough water, though, to be stored. We want this kind of perfect balance of good drainage, but still capacity to store the water for the plants that are living in there. We want soils to resist pests, pathogens, and diseases. We want them to be robust and healthy and functioning. We want soils to be able to help plants make it through stressful events, droughts, high temperatures, cold temperatures, that sort of thing. So we want soils to be able to do all of these things. And in order for a soil to do all of this, have all these functions, it needs to be healthy, it needs to be functioning well. Well, how does it do this? Soil's not just that pile of, sand, salt, and clay with maybe some air and water in it. All of these processes that we're talking about, all these things that we want soil to do, they're all mitigated and happen because of soil biology. And that's where soil health is new than maybe where we were decades ago. All the soil maps that you're using always had great soil physical and engineering properties, but it didn't really talk too much about the soil biology, because soil biology is pretty hard to get a handle on because it is massive and diverse. 1 acre of healthy soil's got 27,000 pounds of biomass. Look at that, 10,000 pounds of fungi. Same with bacteria. Look at all those 1,800 pounds of earthworms, not to mention the algae, the protozoa, the nematodes. All that stuff. Soil is hosting 25% of the Earth's biodiversity, and most of it we don't even know what it is. But we do know that all of it is critical to how healthy and functioning that soil is. So what's happening here is we've got our nice plant growing up top. It's collecting the solar energy from the sun and the carbon dioxide from the atmosphere, and it's doing that magic photosynthesis thing. And it's creating carbon, and it's using that carbon to grow, but it's also pumping that carbon into its roots and out into the soil system. And that carbon that's going out into the soil system is feeding, driving all of the life that's there. So we've got organic matter, living stuff, really dead stuff. And we have fungi and bacteria and arthropods and big insects. And all of it is working together. And all those arrows you see on this picture are all changes of energy from the sun going through the plant, going through the root systems, going down into the soil systems. And with all these energy transformations, you get nutrients released and energy released and carbon stored. So all of this vibrant, robust soil food web is getting us to those functions we want soil to be able to do. So let's think about this. We want high functioning soils that provide all these ecosystem services, and we need them to have these, diverse, abundant, and active biological communities. That's the fourth component here of a healthy and resilient soil. But what other parts of the soil system are important for it to be considered healthy and resilient? We've got to have good surface protection. That could be living surface protection, dead surface protection. That's like a mulch or a crop residue living as a cover crop. We want optimal soil organic matter. Keyword there being optimal. You're not going to compare the soil organic matter in a desert system versus the Olympic rainforest. It's just not in the same ecosystem. But all of the soils that are there and functioning have an organic matter level that makes sense for how they've developed. And we as producers and managers need to think about optimizing the capacity of that soil to have a certain level of organic matter. Of course, we need stable soil aggregates. I love stable soil aggregates. We're going to talk about that more. So these are the kind of 4 components of a healthy and resilient soil. And really, I'm sure many of the listeners today have seen, similar slides and similar pictures, but a real takeaway from today, and a takeaway from all of the presentations you'll hear about today, as people drill down into one particular nutrient or the way systems work together, so we have to consider soil as a habitat. Soil is habitat. It's habitat for all those microorganisms, for all those arthropods. And here on this picture, you see this big root, and it's surrounded by these sand particles, and it's got this little offshoot root and these root hairs. So those big bouldery type things, those are the sand particles. We got our fungus that's in there. And we've got our big Godzilla-like arthropod, right? He's crunching down that pore that's full of air. That's a terrestrial ecosystem that guy is cruising through, grazing on those fungi and bacteria. And then you go pop one pore down below, and you've got a lake in the middle of these 5, 6 grains of sand. And that lake has its own oxygen concentration and carbon dioxide concentration. And that lives in nematode and all these other bacteria that are feasting and living and dying with each other. And it's an aquatic ecosystem. So like you're 1 grain of sand away from a terrestrial ecosystem, an aquatic ecosystem, 1 rainstorm, and the whole thing changes. Soil is a diverse, complicated habitat with so much life in it, so much robust and vibrant life. And all of those processes, the nutrient cycling, the water storage, clay dynamics in soil, all of that stuff happens in the places where the soil isn't. It's in the pore space. So that's why we need really strong aggregate stability, because for all of the cool stuff that we want soil to do for us to happen, we need space in the soil, big pores, little pores, teeny tiny pores, for that to happen. And that's why aggregate stability is so important. So I'm going to pause my presentation so you can see on my camera my aggregate stability demonstration. So hopefully you can see this. I have 2 soil clods. They are the same soil, Willamette Silt Loam from the Plant Material Center in Corvallis, Oregon. And one of them is, because the Plant Material Center is research farm. They do a lot of tillage, they do a lot of disturbance, keep clean seed beds for research. And the other aggregate, and I don't remember which is right next to it from a willow cutting spot. This is just water, and I'm just going to drop the soil clods into there, and they've been in my bucket for a while. But hopefully you're seeing a difference. If I can hold something up, it makes it easier to see. So what you're seeing, one of them, this one right here is staying together. And this one, you can see the cloudiness as it's bursting apart. So what's going on in that system? Oh, a nice big chunk fell out. This aggregate does not have good soil strength. All of those particles, all that pore space is not held together strong enough with the microbial glues and glomalins and polysaccharides to be able to withstand the force of the water coming into those particles, and it's bursting and it is splitting apart. So in a rainstorm, this is going to shatter, it's going to slick across the surface, the water's not going to go in, and it's just going to erode. This soil, same exact soil, same exact composition of sand, silt, and clay, same formation, just different management. This is undisturbed, it's next door to this field, and it has good soil structure, strong aggregates it can handle. You can see those air bubbles popping up. It can handle the power of the water rushing into those pores, and it's holding together. I can leave these up for a week, and this one would stay together, and this one would slowly disintegrate. So what we want are these really nice, stable soil aggregates, and you can do this, when you're doing different tests and demonstrations. Strong soil aggregates is really a synthesis of the soil's physical, chemical, and biological processes. If you've got strong, stable aggregates, you've got all that happening. The physical soil particles are being held together through the chemical processes of developing polysaccharides and glomalins with those microbiology. All right, I'm going to move these out of the way. Go back to my presentation. All right, so we know soil aggregate stability is really important, and that demonstration really shows you the difference between a stable soil aggregate and unstable aggregate, and how you can imagine a soil that has a stable aggregate is going to be functioning higher. Most agricultural soils are somewhere between those extremes. Forest soils, range soils, same. All right, so let's think about this. We want high functioning soils. We want to help folks who are land managers and producers understand things that they can do to support high functioning soils. So we've NRCS, and pretty much around the world, it's different versions of these same principles, has come up with these principles to think about functioning soils. We want maximize living roots, maximize diversity, minimize disturbance, maximize cover. If we can think about any system, orchard, pasture, forest, range, row crop, cereal production, no-till, that kind of stuff, you know, wheat fallow, we can think about any agronomic system or production system and put it through the filter of these principles to see, you know, where a producer is capturing things that support functioning soils and where they have some gaps. And then you can work through practices to be able to address those gaps. And these nice principles kind of go into two buckets. We want to feed our soil. We want diverse, continuous carbon inputs, that energy coming from the sun feeding the soil. We want to protect our soil. We want those aggregates to be stable and we want that organic matter there. And if we can get those things happening, we're going to have high functioning soils. So why do we want to feed our soil? Why do we want to maximize living roots and maximize our diversity? We want to break disease and pest cycles. We want to stimulate change and below ground diversity. We just want that healthy. We want 90% of that stuff that we don't want, no, we don't know what it is. We want it in there. We want the organic matter because that's holding the soil together. That carbon is coming from the plants. We want that tight nutrient cycling, which enhances plant growth and increases predator and pollinator populations. The more diversity you have, the more fighting and the more competition in there, you know, the more you're getting out of that. We want to protect our soil and our soil habitat, our organic matter, by minimizing disturbance and maximizing cover. So we want to maintain those soil aggregates. Soils don't function without stable aggregates. They have to have the space to do all that biology and to do all that chemistry. And we want to reduce runoff and erosion. We want the soil to stay where it is. We want to buffer temperature on a hot summer day in July. Between the rows of bare soil versus covered with a mulch or growing a plant, you can have 50, 70 degrees difference. And when it gets hot in soil, microbial populations slow down. And if they're slowing down, they're not cycling, they're not functioning, they're not living, they're not killing, they're not eating. We want to reduce evaporation, we want the water to stay there, and we want to maintain that soil organic matter by minimizing that disturbance. So let's continue. Obviously, we are making connections here between soil health, water quality, food safety. I'm going to be speaking more about the water quality. So this is setting us up for what you'll hear the rest of the session with some of these big picture connections between high functioning soils and clean water. And we can break this into these two categories again. We want to feed our soil, we want to protect our soil. Again, feeding soil is keeping a living root and having diversity above for diversity below. Practices that support feeding soil are cover cropping, you know, putting crops, having the soil constantly covered, conservation cover, strip cropping, crop rotation, changing what's growing in time and space in that field or in that system. And that's going to give you a healthy root system that's supplying lots of energy to build organic matter and cycle nutrients. And that diversity above is going to give you lots of diversity below, which is going to give you lots of different organisms that from a water perspective, those organisms will be able to capture and break down pollution. You know, soil, those 90% of things that we don't know what they are, they eat everything. We haven't found something yet that we can make as humans that some soil organism somewhere won't decide is breakfast. But we have to have the organisms there and functioning and active, which you get when you have a lot of diversity, so they're around when the thing we want them to eat is there. And that tight nutrient cycling that we get when we have cover cropping and all that energy coming into the soil, so that soil is always getting that carbon source, so it's always, those microorganisms are always kind of hanging out and living and functioning, gives us that tight nutrient cycle, which keeps the nutrients in the soil system as opposed to exiting, either as runoff or down below as water through the waterways through the water column. Feeding the soil, then we want to protect the soil, keeping the soil covered, minimizing disturbance. Practices that support keeping the soil covered and minimizing disturbance include cover cropping again, mulching, residue management, again, all scalable depending on if you're in a home garden, in a high tunnel, a 3,000 acre grass seed field, 3,000 acre wheat fallow system. We want reduced tillage or no-till. You can get contour buffers, field borders, all these different ways to keep the soil covered, minimize your disturbance. Good cover protects from erosion. That's it. You got to put something between the raindrop or the windstorm and the surface of the soil. That raindrop is falling at terminal velocity. It wants to hit that soil. If it hits that soil, bare soil, it's got so much energy, it just shatters the particle. But if we put a crop or a mulch or a residue between that raindrop and the soil surface, it dissipates that energy, and then the soil stays in place. Plus, keeping the soil covered slows it so the water can get in, it can get stored. Minimizing disturbance gives you those strong aggregates who are able to be resilient against disturbance, and again, create that space that water, those big pores, little pores, small pores, water can get in, drain freely what we want to drain, and then store what we want to store. And from a clean water perspective, obviously reducing erosion and runoff itself is removing a pollutant, and of course also all the little pollutants that are carried on the sediment. So the sediment itself is a pollutant and the sediment carries pollutants. And we can increase the hydrologic function by storing the water more. Soils that can store water more can release slowly over time, so we get the hydro periods to look good. I shouldn't say to look good, look like has functioning as well as we can hope for them to function. All right. That is your quick overview of big concepts. What is soil health? What do we mean when we say soil health? The 4 principles of soil health: feeding and protecting soil, why that all matters, what we want soil to do, and then some of those large connections between high functioning soils and clean water. I look forward to any questions and answers during the live session of the live part of this presentation. Thank you so much.